Also, thank you for having a short biography read for me. Uh, Now, in fact, this lecture that I have, it is on the topic peer-to-peer energy market between electric vehicles. And to mention here that this work has not been carried out by me, basically. Yeah, the authors of this work, it is given on the slide. You can see them. But this work is a part of one of the book that we edited actually. So I have one book edited on electric vehicle published by IIT with Justice as one of the editor. So I thought that maybe I can present one of the chapter which was published in the book. In fact, if I remember the discussion with Dr. Vijay, he referred that he had sent invitation to Justice to deliver a talk during this FDP program, but because of his because today it is 25th December, so they have good, you can say they could be busy. So then we thought that okay, I can have this chapter presented in this FTP program. Yeah, this is how I move on to this topic. Actually, I want to say. So it is possible that many of the points, if you have some queries related to my presentation, I may not be able, but I will try my best to deliver. Thank you. I move on to the next one. Now, as an introduction part, we know that we have several advantages towards the electrification, mainly for the transportation, road transportation. But it is also important to know how the large scale deployment of electric vehicles will have impact on the existing power system. So now, in respect to the challenges, we want to know how this large-scale integration of electric vehicles will have impact on the grid, because this could lead to an increase in power losses. You may have voltage drop. There could be voltage unbalance as well. Then you have overloading the transformer if you have charging of electric vehicles at a specified time duration from all the drivers. And then again, there also harmonics being generated in the line, in the signal. So in general, uh, then to large scale integration results to deterioration of the power signal. So we have the decrease in the power quality at the distribution gate level. And then if you refer from the generation side, their deployment can also increase the peak demand, and also then thereby having a challenging tasks, mainly from the system operator point of view, I say, towards the balancing of electrical power need requirement. Uh, with these challenges that we face across towards the integration of large scale integration of electric vehicles. So what are the approaches or the scope that we can consider? Uh, Traditional way to reduce these negative effects can be towards developing some smart charging algorithms, basically, so that we can flatten the load profile, basically, so that we don't have increase in the peak demand in the given time slot. Then with this scheduling for the electrical charging can fill the valley part of the load profile. And then, as I said, it can avoid the peak demand, and then we can have better use of the base load power generation units. That is basically the traditional approach that we can find against the negative effects for integrating the electric vehicles in the system. However, now recently there had been talk about we can say peer-to-peer applications basically. And in that respect, because these peer-to-peer we have come across in several applications. It could be like online auctions. Then you have, let's say, for car sharing. Also, we have talked about then taxi cabs, parking lots, spare rooms, and so on. So these peer-to-peer applications have been heard throughout the world in several forms. Yeah, and recently some of the companies in the European, mainly I refer to the European example, so they have allowed to connect the power producers and the consumers directly without having the, you can say, to a large network, but that is, you can say, establishing a new set of a network or the scale and escape for electrical power sector. Uh, in respect to the peer-to-peer for energy applications, they have been at a small level. Sorry, at a small scale, mainly when we have renewable resources with the consumers and who are interested to buy cheap power from the generation companies. And then peer-to-peer energy trading have been talked about between the electric vehicles here. And that is one of the approach which can help to reduce the demand uh, during the peak hours, being we can say the peak tariff hours. So this is what I will have in my discussion here in the presentation. So we have an activity-based model, and to work on this activity-based model, we actually set certain objectives here, and we say that what is the total energy available in the batteries of electrical vehicles and which is surplus in those batteries of electric vehicles, and at the end of their daily trips. So that means you have set A of those batteries of electric vehicles which have the energy available in their battery even after the end of their daily trips. That is one part. Second part is that some sets of the batteries of the vehicles, they have the energy demand, and thus they have the lack of energy at the end of their daily trips. And so that means it is possible that some of the electric vehicles they have to travel for a faraway distance in their daily trips, and then the energy which is available in the battery is not sufficient to meet their daily trips, and thereby they need to have some intermediate stage charging during the day. So those we have set it as set B. So set A, energy available from the batteries, and set B refers to energy demand from them. Now we want to determine what is the mobility patterns in the region. That we have to understand this part, how the drivers or the owners of the vehicles, what is their behavior in the mobility here. Then activity-based models, we work on travel demand, and this is based on the activities associated with each individual in the whole population that we have to consider here. And we also have consider household and other community infrastructures. It could be like the requirement for the schools and the shops, and how they are going to influence the travel and the activity behavior of those drivers. So all these parameters have been considered in the study while building the activity-based model. Yeah. Uh, Now, this model uh, will have the use of is actually an acronym feathers. It is basically the forecasting evolutionary activity travel of households and their environmental persons, which was developed by the Transportation Research Institute from Hasses University in Belgium. So this model will have the use of this feather facility, and this model is fully operational in the Blanders in the Belgium region. But and again, it has been also planned to have been to be applied in other countries, and some of them are listed here. This model is used to predict the time-dependent electric power demand for the Blander regions under the specific assumptions with the electric market share here. To give you more information, what is the Feather project? Feathers, they generate a daily agenda for each individual of the population, and this each agenda will consist of sequence of episodes for each of them. So as you can see that this is a typical agenda defined for an individual. It could be slightly different also. So here they have defined what is the time slot for the sleep, and then between this period they are at home, and then they have the use of the car. So that means during this period they will drive to their office, and then during this period they would work in the office. Yeah. And then in some cases they will have to again drive their car, and then they may go for shopping, or for it could be some other activities involved for them. And then there is some period time slot where they don't need to have the car, but they just walk down. And then again some other activity related to the leisure. And then finally at the end of the towards the end of the day they have the use of the car driving here for a certain period, and finally they are at home. So throughout the 24-hour, as you can see, so they have certain activities involved, and then they have been driving their car. So because during when they drive the car, they cannot charge it. All right, but there are some activities which we can consider in developing the algorithms, so that during those periods, so we are able to charge their vehicles. So that is the typical agenda which we have defined for individual as per the feathers model. Now this strip belongs to a certain region actually. Or it could be a small zone, we call it a traffic zone in the Flanders region, and which has an area of something 5 kilometers square here. And now this model will have a daily agenda forecast. So that means we know what could be the activity of each individual in the region. And then prediction on the outcome of the decisions which is to be taken by each individual. That is again we are able to get from the feathers model. And this model covers the complete planning and the scheduling stages for those activities. So that means each individual, how they are going to plan, how what will be the schedule, it will be all available to us from the feathers model here. And then in the scheduling stage, we know what will be the sequence order of their activities and what will be the timing of their activities. That is known to us. And then how they are going to have the uh, use of their transport. I mean, the use of their car. That means during the which time slot they will have the use of their car. This information is available to us. And some of the daily activities we say as mandatory, it could be like we have said, okay, because we were like work, going for work, going to office, school, or then I got pick up drop for the children, etc. So these activities we have considered as a mandatory, and then some other activities they can be as a discretionary, like say for going to for leisure shops. So that will another one. Yeah. So all these activities at an individual level of the population in the region, traffic zone region, we have defined here. Now, but this for the model has the data for each individual and they are independent of each other. Uh, except the all the members, except for the members within the same family, you can say, right? And we have the coordination constants, input data, and then we apply some data mining algorithms, which are available in the feathers model. We define the agendas of those agents, both at transportation level and their timing. So with this data available to us, we will work on how to develop the algorithms for the times for the most appropriate time slot for the charging of the vehicles here. Now, as you can see in this slide, uh, uh, we need to have the decisions to be taken by the agents for the data driven, and but this is more or less as a stochastic process, and that will require the use of decision trees to be trained by the data which we have collected actually. And this decision trees training will have the use of research mobility behavior, which is actually a organization which is responsible for developing this behavior model. And based on their data collection for the Flanders region, we work on this one. So we do this survey. Then we have the consensus data, which is used to generate the synthetic population of the model. And we also have some data related to because land use data, that means which traffic zone region have how many individuals or inhabitants in that traffic zone region, how many shops we have, the number and the size of the schools, then again the office hour and the number of the offices organizations or the job opportunities available in each traffic zone. So all this data which are available to us. Then we develop some transportation impedance matrix, and for wherein we have the characteristics of the transportation network for different types of the mode. It could be like car, it could be train, bus, bike, etc. And they are now referred in different travel times actually between the traffic zone, and considering the peak and the off-peak periods here. So that is the overall model which I talked about in the previous slides on activity-based model, which actually this figure shows the how does the data would flow in the feathers activity-based model here, right? Uh, this model which we have, they are stochastic. So as I said, we have the use of some synthetic population data as well here. And for this, we have the use of Monte Carlo simulations so that we are able to have prediction. They are with the comparing with the data aggregated ones. And once all these daily agendas for each individual of the synthetic population are available to us, then we determine the number of commuting trips that can be driven by battery only electric vehicles for those people living in the particular zone, traffic zone. Total energy demand uh, by the aggregation of these consumers for each traffic zone. This will be during the working hours that we have worked out here. Next, we work on to develop the consumption model. So, in fact, there are different models already available in the literatures. Yeah, but in the framework for this study, they have the mobility model use, which is based on the traveled distance, and this is as a output data actually. And this consumption model is being generated based on real consumption of five different models of electric vehicles which are sold in Europe. And then we analyze the real consumption for more than 270 electric vehicles. So you can see here in this figure that on this side, y-axis, we have the number of vehicles, and on the x-axis, it is the energy electric power consumption kilowatt hour per 100 kilometer distance traveled. So we have the, as I said, we have some different models of electric vehicles which are in the European countries. So you can see Renault, Nissan, BMW, and so on. So now with these different models of electric vehicles which are available, and we worked on that, then how many number of vehicles of different models they are available, and then how much energy do they consume for per 1100 kilometer. We find that average consumption for these vehicles is something about 15.5 kilowatt hour for per 100 kilometer. And with this, because each of the models here, they have different, they are different in number, and as well as the amount of energy consumption, that is also different actually here. So the total consumption for these vehicles, for that we have obtained an approximate curve actually, and that is by normal distribution curve here, right? And we have actually randomly selected consumption sample that has been used to estimate the power consumption for a single agent in the mobility model. And we have, though, some assumptions in developing the consumption model. Uh, First assumption that we have considered is that those drivers who fulfill their daily activities without modifying their scheduled trips. Right, so we will consider only the drivers of those electric vehicles uh, who, who complete their daily activities. Let's say that they go for the office, then they go for the shopping, and then they go for some leisure activities, and then they go back to their home and then keep their vehicle parked in their at a parking site in their home. That is one. So that means their daily activities are not disturbed throughout their daily routine time. I mean, so we have considered only those drivers, and they will be as set A and set B actually. Then that means those drivers who fulfill these their daily activities, which is being predicted, right? So they will be only considered in the category of set A and set B. Second assumption that we have is that all electric vehicles they are recharged during the night of peak hours. So that is, we say that all the vehicles will get recharged during the night hours, and their batteries, we assume that their batteries are fully charged before they start their daily trip in the morning, right? So we assume this one that before they start their daily trip, their batteries are fully charged. Then we third assumption we say that the constant electric energy consumption throughout the day, right? And again, it only depends on the travel distance according to the data. So we say that the amount of energy consumption along the day throughout the day that is constant. As an example, to validate the algorithm, we have said that the nominal battery capacity is 24 kilowatt hour, and we have considered the model from Nissan. And for this case, the effective battery capacity is something 20 kilowatt hour. So we have a little bit higher battery capacity, but the effective capacity for the Nissan Leaf model, it is something 20 kilowatt hour. With these assumptions, uh, now on this slide, if you can see, we find that this is the battery, and then we want to charge the battery of the electric vehicles in the car. So we say that this is the nominal capacity of the battery. This is something 24 kilowatt hour. But effective battery capacity, we want to charge from to 0 to 20 kilowatt hour only. So that means the state of the charge, the battery, in the algorithm, it will become 0, right? And it means it is the minimum one. Still, but knowing the fact that there is still for 4 kilowatt hour remaining, but we don't take into account the remaining part here. So if it is fully charged, then the state of charge depleting, and as it reaches to something 4 kilowatt here, then we say that state of charge is 0% here. We have this assumption applied in our algorithm. So we don't say that the battery is completely drained out. We don't say this one. And according to this mobility feathers model, there are, you can see how many number of the vehicles you have, which will be driving daily in the Flanders region here. So it's a huge number of vehicles driving daily in the Flanders region here. Now, with this one, we have actually, as I said, that only those drivers of the vehicles who do not change their daily activities, which was predefined. Uh, uh, we have considered them in the category of set A and set B, right? Now, as per that, we have actually drivers classification based on their mobility behavior. The so with this, uh, so we have set A. So we consider those electric vehicles which can complete their activity, which can complete all their daily activities uh, with the energy recharge only during the night hour. So that means you have some sets of electric vehicles here And these sets of electric vehicles, they have full charge battery, right? That means they have charged their car, they have charged their electric vehicle when they have parked at their home. So the battery is completely charged before morning. During the night, they have charged it. And now they drive and then they go for their activity from, let's say, from the morning till evening. And by that time, but however, in their case, the depletion in the state of charge, you can say, it is very low. So that means they don't have to travel much. They go for the activity but they don't travel much, and thus there is some amount of energy is still stored, is still remaining in their battery where as they reach to their house. So on the reaching to their house, they will again charge it for the next day trip. That is possible. However, we have another set B. So in this case, they are for those owners or the drivers who require to charge, at least at one intermediate point. So that means you have some sets of the owners of the electric vehicles who get their vehicles charged when they have their electric vehicle parked at their house during the night hours. So before they start their daily trip, they get their vehicles charged, so that is full charge. But they have to travel to a large distance. All right, that could be one way. So and thus the amount of the energy which is available in the battery, it gets fully discharged, and thus they may require at some place during their daily trip to charge their battery, right? And then again, to reach as they reach to their house, then again the battery is fully discharged. So that means they need to have these sets of the drivers or the vehicles owners, they need to have some intermediate charging periods here. And that could be recharging could be when they park their vehicles, when they carry out their activities. So that is during the parking, when they carry out their activities, so that is one time slot where they can charge their battery. Then we have another one, but though not considered here. So there could be another set C for those drivers who could not complete their daily trips. That is one with an electric vehicle without modifying their current mobility behavior. So there are still some sets of the owners uh, who are not able to complete their daily trips without modifying their current mobility behavior. So that is one part here. Some sets of the vehicle owners there could be. That means some group there would be, but we have not considered them in our algorithm. Now this what we have, it could be reason that because for these owners, for these drivers of this group, they may have to total distance of travel which is much larger than the maximum range of electric vehicle which is available. So that means they have to travel to a large distance with respect to the amount of energy which is available. So that could be one reason for this category. Then another one is that the time which is available during the day to just recharge, that is very small. All right, they don't have, that means sufficient time to recharge their battery during the normal activity. That is very for short duration. So and thus they need more time. Thus they need more time to charge their battery before they reach to their house to recharge during the night hours. So, but these are under the category of group C here. Uh, Now, in respect to the Flanders region, for the time zone, for the traffic zone, I mean, we find that most of these we refer to the set A, right? So in this case, most of these vehicles they travel for very short distance, yeah, during their daily trip. So thus they have they start they before they start their daily trip, they have full charge battery. They travel, but the travel distance is short here during their daily time, and thus they consume small amount of energy, and they have high amount of energy still stored in the battery when they are at home. And we find that in the Flanders region, we have about 200,000 vehicles, which can store more than 18 kilowatt each, right, at the end of the day. And thus the total extra energy which is available in a store form, that is something 13.246 megawatt hour. So that is the total amount of energy which is stored in these vehicles when they are at home. And in this histogram, as you can see, it is reflected actually. So we have the number of the vehicles in the Flanders region, and then the amount of the energy which is surplus, which is stored surplus after they have end their daily trip. Right. So we find that this part, so they have huge amount of energy is still remaining when they have completed their daily trip, and when the vehicles are back at their home. So we can see that there is huge amount of energy available, and the number of such vehicles that is also large here. That is, you can say, the feature or the characteristics of the owners or the sets of group A here. Similarly, if you look at the consumption model for that we have defined for set B, in this case, we find that as we said that they will have the need of additional energy required by these vehicles to complete their daily trip. So as you can see here, so they have the vehicles at their home premises parked, they get the battery charged, but while performing their daily trip, the energy is fully discharged, and then they have the need to recharge it here, so that they can complete. So that that means they need an intermediate charging before completion of their destination trip here. And most of these vehicles they require a small amount of extra energy to fulfill their daily trip, as you can see. So before they reach back at home, so this is the amount of energy they can get charged at the intermediate stage, and then as they reach, they get complete, the vehicles have their batteries completely discharged. So as for that, you can see here for the set B, the number of the vehicles in the Flanders region, this one. However, you can see that the amount of energy which is required to complete their or to fulfill their daily trip requirement, that is, you can say, very less amount actually here. And thus, total energy demand of electric vehicles during the day, that is something 366.67 megawatt hour. That is the amount of energy demand by the category of set B here. Now, with respect to this, this is, you can say, the amount of energy which is surplus available. And then from the set B, this is the amount of energy demand. And you can see here that this is something much higher, and it will be something 36 times more energy which is stored in the battery for the vehicles of set A with respect to the demand of the battery from the vehicles of set B to complete their daily trip. So that is where we need to work out. We need to work out or develop algorithms how effectively we can have the some kind of energy management for the charging period, because these owners of the vehicles of set B, they will like to have the charging of their vehicle at the intermediate stage at a minimum cost. So that is what they will like to have. That means they should not have they should they may not have like to pay more energy to charge their vehicle when they have it somewhere here or in the mid of their daily trip. They may not like to have it, and it should not be more than the electricity price during that time slot. So thus we need to have some kind of a strategy or the algorithm develop how we are able to have minimum cost of recharging for the owners of the set B here. With this model available, next we have we have as I said that we want to have the model developed to minimize the cost of for the set drivers of the set B. But again, the drivers of set A, they will like to have maximum profit because when they have to discharge the battery, right. So then in that case, they want to have maximum benefit out of it. Right. So, but then that means we need to have some optimization stage in the development of the algorithm. So, and with that, we have to keep in mind that the electricity price it varies actually every hour. That exists in the European system. So their electricity price every hour it varies actually, and it is important for the users to know where, and that means at what time slot and in which zone and in which traffic zone will be convenient for them to recharge their vehicles in advance. So that means this is what we are saying. It is with respect to the drivers or the owners of set B basically. So they should have sufficient information that in which traffic zone and in at what time slot what is the amount of energy and so that they can recharge their vehicles, fulfilling their daily agenda without needing to modify their mobility behavior. That we have to consider, because it is their agenda that okay, they have to go to this office for work, and then from there they have to go for the shopping, or they have to go to the school to pick up or to drop their children. So that is as a agenda activity, so that they cannot modify. It is in their mobility behavior. All right, it is in their agenda items actually. So without modifying their mobility behavior, they have to know at what time slot and in which zone, what is the amount of energy available, cost of the energy available, and what could be the time, and which could suit to them for to recharge their vehicles actually. So all this information should be known. Here we make an assumption that this variable electricity price is known to us, although it we know that part, because nowadays we have the system which can say what will be the amount of electricity price in 1 day advance. So that is now it is possible day ahead prediction of electricity price, it is now being possible. Then again, the second assumption we had that taken into account the daily agenda of each driver, and that is provided by the feathers model basically. So with this prior information, prior data available uh, to the drivers, then the vehicle owners they have to optimize their daily energy cost. uh, that means, and that will be possible to schedule, that means where and when they can charge their electric vehicle at a minimum cost. So that is one way. Yeah, right. Now in the first part, we have the battery recharging needs for the drivers of the set bay. So as I said that because we as the drivers of the set bay will like to recharge their battery at a minimum cost. So that is to be addressed first. Then each driver they will look for to minimize the recharging of the battery cost actually. So this is how we have defined the objective function, and this is the electricity price, grid electricity price, and then this is the amount of energy extracted from the grid to the vehicle battery. And then this will be the time of arrival, in fact, and departure part here. And but this objective function will refer to some constants. That means, and the first constant is the what should be the minimum state of charge and the maximum state of charge. So if we refer, we have considered 0% as the 4 kilowatt hour. So that could be the minimum scale, and then maximum up to 24 kilowatt hour here. And then with this equation, when you say here, equation number 2, that ensures that effective battery state of charge, which is variable over the times over the time period. And then if you refer to the equation number 3, uh, that actually imposes the charging rate limit, and that is the maximum P max actually, which represents the maximum power available for charging at a charging station, which is in kilowatt. And del T is the time length or the time slot, which is which we apply for the algorithm to charge the vehicle here. That is for here. And eta C is the, you can say, the charging efficiency rate, right? And then if you look at question number 4, this one refers to the what you say as dynamic evolution of the battery state of charge, where you have the current state of charge, which is equal to the previous state of charge, plus what is the amount of energy injected into the battery during the charging stage. My difference of the energy consumption due to the driving activity, which is in kilowatt hour. Yeah. Then if you refer to the equation number 5 here, uh, because it is possible that charging process is not 100% efficient. So this constants will determine the relationship between the effective energy injected into the battery, and then the amount of energy extracted from the electricity grid. Right. So this is the amount of effective energy extracted from the electricity grid actually. In that respect, it is given. And then the last one, the last equation. This is actually initial condition of the battery stage of charge when it is fully charged. just before the departure time in the morning hour. So that means what is the state of charge when the vehicle depart at the morning hour. So this is 20 kilowatt hour. That is the maximum which we have considered here. So with these constants defined, then these equations they form a linear optimization problem, and they are solved using GAMS and CPLAC solver for each vehicles from the set B. Now, main decision variable which we have, it is the this one current, and it will depend upon the availability of electric vehicles to charge at this point. Uh, with this here in this table, uh, constant problem for value has been given. So departure time slot is starts with the value 1, and the arrival time slot it is with 96. So the entire 24 hour. So we have a 15-minute interval basically, that is delta t to run the algorithm. That means the time length of each slot it is 15 minute here, and thus we have to altogether 96 time slots. Then maximum state of charge we have set 20 kilowatt hour, and minimum we have set it as 0 kilowatt hour. And then the maximum P max power available on the charging station, available at the charging station, that is something 3.3 kilowatt hour. And the efficiency, charging efficiency rate, we have the zoom 0.95 here. So with these values as given in the table, yeah, the complete day is divided into 96 time slots, each of 15 minutes. First period starts from this hour, and then the last one is from 23:45 hours to 00. It can be extended for certain amount of vehicles which arrive at a later period. And then the state of charge effectively is between 0 to 20 kilowatt hour. And as I said, the maximum power available at the charging station is set to 3.3, and this corresponds to 16 ampere socket in a 230-volt single phase system. With this power limit, the maximum energy extracted from the grid in each time period of 15 minutes can be of this much energy, 0.825 kilowatt hour in 15 minutes. So here we have the figure to illustrate how we are going to have this algorithm being implemented for the car owners of set B here. So as you can see, on this side you have the state of charge, and this side you have the time slot, and then again we have the electricity price given. So you can see that the first step we start from you can say about 6:45 hour to 7:30. The first trip takes place, and the travel distance is something 12.73 kilometer. So during this period, the car moves. And before the car departs from the home, we say that the battery is fully charged. It is 100% here. So before the departure of the vehicle, so it is 100%. And then the owner goes for work. So this is the first intermediate stage where it is possible to recharge the battery at it could be in the parking lot. So that is one way. And then second trip that take place as indicated here, it is something 12:30 hour to 13:45 hour something here. So during this period, the second trip take place, and travels for a distance about 59.48 kilometer here. Then they have some activity defined in the agenda for the individual. So that is, let's say they go for some shopping, and at the shopping you have a parking space, and then it is also there it is possible to recharge their battery during the second scheduled stop. So that could be another possibility here. Then they travel back, and then that means they drive their car, and then they travel for something distance 44.85 kilometer, and then they reach home here. So when they reach home, then there it is possible that they can charge the battery. That is possible. Now when you look at this one, so you have actually the total consumption. It is something 22.12 kilowatt hour, which is actually more than 20 kilowatt hour that we have assumed. So that is the actually the amount of energy which is required to complete their daily trip agenda, because in the agenda they go for work, they work at office, and then they go for shopping, but they have to travel these many distances in between. And then to complete their daily agenda, they have something about 22.12 amount of energy being consumed, and thus they require some intermediate recharging here. And you can see that when they travel from when they depart from home, so during this period, so the state of charge of the battery decreases here. So that is one part we should understand. It is indicated here. And then it is possible that during the work, when they have their vehicle parked in the parking space, they can get their battery charge. So thus the state of the charge of the battery increases, and then let's say it become constant. Yeah, that is one part we have considered, but we will discuss about this a little bit more later on. And then uh, for the next stage of the agenda, then they have to travel for 59 kilometers something, and then the state of the battery decreases. Yeah. Then again at the shopping complex in the parking space, they can get their battery charge here. That is one. And further they drive back home. So then while driving back home, so their battery gets completely discharged, and thus when they reach home, the energy level in the battery, it is completely zero here now. So that is and thus that means they don't have any energy left when they reach home here. Now you can see that this is the electricity price which has been varying over the complete time slot. Now, what could be the time slot, right? What could be the time slot when the owners of the set B will require or will have the need to charge their battery? Because because you can see here that for every time slot, the electricity price has been varying here. That is varying here now. Okay. And this is the pattern of electricity price which has varied over the 24 hour, right? And now, which time slot will be more preferred, right? So because this is the time period when they can charge their battery, and this is the time period when they can charge their battery at the intermediate stage here, right? So you can see that during this period, the least energy cost was somewhere here, right? Because at this hour, during this hour, energy cost is maximum, right? And then again, when you look at when they have their parking vehicles parked at the shopping complex, then the energy cost is least over here. So it is possible that when the electricity price from the grid, when the electricity price of power which is available from the grid is least, when they have their vehicle parked either in the shopping complex or in their office is minimum, then that could be the suitable time slot when they can charge their battery. So as indicated in this figure, So it is only in this period the owners have preferred to charge their battery, and thus the state of charge has increased. Because during this period they may not prefer, because the electricity price is much higher, so they may not prefer here, right? And same way, when they have their vehicle in the shopping complex park, they may not prefer to charge their vehicle during this time slot, all right, because they will always prefer when the electricity price is lower. So thus, they are during this time they have preferred to charge it. And as you can see that at the later stage, the electricity price increases, so they have not preferred to charge it, right? Okay, so because they want to pay minimum cost for recharging their battery, so they have not preferred it actually. So now this is the time slot which is more appropriate to charge their battery with electric power from the grid here at the moment. So this is one I have said, and then second one, as I said, it could be something here. But this is the case when they charge their battery from the with the electric power from the grid actually. Now with this, owners of these vehicles, they can schedule their daily charging periods in advance. They can do, and thus they can know when and where they have to recharge, so that they have to pay minimum cost to recharge their battery. Now, and this could be possible to with this it is possible to know what is the total energy demand, because owners of the vehicles can schedule, and thus we can know what is the total energy demand in each traffic zone, and again in each time slot. That is possible, and thus total demand of energy can be solved with the optimization problem for the electric vehicles belonging to the set B. And in this graph, in this figure on the slide, it is shown that it is for this traffic zone number 904. We have the total energy demand, as you can see here, and then again, what is the electricity price here? So it is at this traffic zone indicated, and you can see that this is the maximum demand of this much 1.3 megawatt hour, which is somewhere around 315 hours something, and then here you have electricity price indicated, and you can see that uh, the electricity price during this period it has remained low, and that's why since the electricity price has been low, and that's why you can see that the demand is much higher during this period here. That is, you can say, the characteristics of the demand and the electricity price in the region actually. So with this, if we consider for the time slot 15 hours, then we can aggregate the complete energy demand at 15 hour. So thus we can have the lowest hourly electricity price, which could be, and then higher demand, which are, now as in this case we can have actually a spatial distribution of the demand here in the complete region. So this is shown for Flanders region around 15 hours. So you can see some, there are red spots, and then some they're deeper red, and then some of them are the blue spots here. So these higher demands, they are actually indicated by the red areas here. So that is especially a special tempograph indicated here, and total demand at 15 hour for this traffic zone, it is something 1.3 megawatt hour here. And we can also see that total energy demand from the vehicles of set B, it is something this one. And what is the amount of energy which is stored, which is available in the batteries of the set A, it is this one. And we find that thus the energy which is available in the batteries of set A, it is at this zone in during this time period, it is much higher than the demand that we can indicate, that is indicated here. So thus, instead of having the electrical power from the grid, instead of having the electrical power from the grid to recharge their battery, the owners of set B, the owners of set B can charge their battery from the set A, and that is actually we say peer-to-peer battery charging. And thus how to frame it, how to develop a trading system. That means now we, since we find that the owners of set A, they have more energy, they have surplus energy available during this time slot in this traffic zone area, and there the demand is this one, and thus uh, what should be the energy transfer, how we should develop a peer-to-peer energy trading between the owners of set B and set A, because owners of set B will like to pay a minimum cost. They will not pay more energy cost than the one which is available from the electricity grid actually, right? So in that sense, we need to have what should be the minimum cost for recharging the batteries of the set A. But again, the owners of set A will like to have maximum benefit, maximum profit actually, right? So with this, now we want to have a trading system develop, and uh, why one? Because we want to reduce the impact of recharging electric vehicles on the grid, and we want to develop a platform uh, between the producers and the consumers. And you can say the producers are those which are the vehicles of the owners of the vehicles which have excess energy in their batteries, and consumers are those which demand the energy for their daily trip to complete. So with this market system to be developed, we say that at the beginning of the day, the drivers from set B will like to optimize their daily charging, and it will be individually done, but they have to know when and where they have to charge it. And this is the objective function. It is the same one which we have defined in the previous slide, this one. And all this individual electricity demand, they are actually added, and then we know what is the total aggregated spatiotemporal demand being generated in the traffic zone for a given time period, that one. Thus, the total demand energy, this can be provided to the vehicles of the set B, and that could be in two different ways. One is that the conventional power grid, the current day traffic, they can have the information being shared. Another one is that it could be from those electric vehicles from the set A, which are parked at the same time in the parking space, and then they can share the information about what is the surplus energy available in their battery to the owners of set B. So that this it would look like something this way, basically. So that means there has to be an agreement between the producers and the consumers, yeah, on electricity price, how much energy should exchange at a given time slot and in a time traffic zone to have a bilateral transaction. So if I say that you have some sets of the vehicles already available in a given traffic zone, let's say in the parking space, so they have surplus energy at a given time period, and then and there you have some sets of the vehicles which are in the same traffic zone, and then with those informations we can have the energy exchange between the vehicles which are available in a given traffic zone. So, but again, that means it will all depend upon the agreement between the owners of set A and set B here. Now, but again, in this peer-to-peer trading system development, we should see that the drivers of sector, they will have limits, actually two limits to sell their energy stored. The first limit is the, we say, as the lower limit. This is the maximum value of the off-peak traffic, right? Because this represents the price which they have paid for night charging. Because the owners of Sete, they have paid to charge their battery during the night hour. So how much cost they have paid during the night hour charging? So that is the lower limit. Because if they sell their energy from the battery at a price lower than this one, what they have paid it from the for charging their battery from the main grid, then they will be in the loss, and that is the lower limit, and this is the maximum amount which they have paid it during the night hour. Maybe I will discuss this more in the later slides. Then again, they have a lower limit, that is actually the P min, which will be considered to be same throughout the day actually, and will be constant. Then again, the drivers of SETA, they want to, as I said, they want to have maximum benefit, maximum profit, because they will also willing to sell their store energy at a higher price. They will also prefer, right? But this value, but they cannot because they may not be able to sell their stored energy at a price more than electricity price. All right, because this will be limited by electricity price. Because if the owners of set sell their stored energy at a price more than of electricity grid price, then definitely the set B owners will try to recharge from the main grid rather than having their battery charge from the drivers of set A basically. So in that sense, this is the limit on the drivers of set A, because they cannot have a higher price. They cannot have a higher price set than the grid price at the same time slot. That is the P max actually they have set. Then again, they cannot have excess energy being discharged from the battery, because they need to have some amount of energy which is available in the battery, so that they are able to reach back to their home. So that means how much energy they have to trade, that is also important. That means how much energy they have to share in the trading, this is also important, and that's there are limits here which the drivers of set A have to take care of it. So with this one, as to refer in this figure, you have it, this one electricity price, and then here we have the time slot, and we have the vehicles offset there, and you can see here that uh, up to this one, let's say this is 6 o'clock. So up to 6 o'clock, from the night hour to 6 o'clock in the morning, this is how the electricity price has varied, right? And during this period, the drivers of Sate, they have their battery charged, and they have paid this much amount. They have paid this much amount to charge their battery, and that is the maximum amount. In fact, this one, because they have paid maximum amount for the charging during this period, actually, right? This one, and this, as I said, this will remain constant throughout the day, right? And then you can see that the grid price is varying. The grid price is varying throughout the day. Now, so because, and that means this is the price which they have paid to charge their battery during the night hour here. So this is for the set A. This is the amount of energy which they have paid actually. However, with respect to this one, with respect to this one, now the drivers of set A, if they want to have the maximum benefit, right? If they want to have maximum benefit, now they can agree to discharge their battery during this time slot, because here the electricity price is this one, right? So they may agree to discharge their energy during this hour. So this will be the difference of in a cost which they can benefit. And if I say if it is during this hour, so this is the maximum profit that they can get. And if I say during this hour, this one. So for each time slot, they will have their difference. They have the different benefit. They have the different benefit, and thus they have to decide during which hour they can trade, or they can discharge their battery, and thus they can have peer-to-peer trading with the drivers of set B. It will be different. And thus, as if we refer to the in the previous, because we are taking the example of 15 hour. So during the 15th hour here, you can see that at this point during the 15 hour, that is the amount of energy or the electricity price which they have, and thus they can have the maximum benefit which they can get. Now they cannot the drivers of set A cannot have the price for the discharging greater than this value. Otherwise, if they keep, then the drivers of set B will get their battery charged from main grid rather than from the drivers of set A actually. Right. So thus they have to keep a minimum price. The drivers of set A have to keep a price lower than electricity main grid price actually here. Right. And thus, as I said, if the drivers of set A, they try to sell the energy at a higher price than the P max which is available, right? Will drivers of set B buy from them? That is the question. So no, they may buy the electrical power directly from the main grid, because that is the electricity grid price here, and that will be cheaper for them. That will be cheaper from them to charge their battery. So that the drivers of set A, they have to take care of it actually, how much price they should keep for peer-to-peer trading with the drivers of set B here. Now, how much energy should they trade? Will be the important one, because they also need sufficient energy available in the battery, stored in the battery, so that they can reach their home. Because they also have some agenda defined in their daily trip, so they must know how much energy they can trade. Now, with this one, as you can see, so we have the drivers of the set B. They will be willing to pay less, right? And with this, we have some assumptions saying that preference will be for charging from peer-to-peer trading rather than electricity grid price. And and if in case the electricity price for peer-to-peer trading and the main grid price, they are equal, then the drivers of set B will charge from peer-to-peer trading basically. And they will charge directly from the grid if the peer-to-peer trading price is higher than the grid price. So if in case the drivers of set A, they try to sell their stored energy at a price higher than the grid price, then the set B, drivers of set B will charge for directly from the grid. That is, we have some assumption here. So with this, the total amount of energy demanded by all the vehicles from the set B in a given traffic zone, we can know here. And let's say it is given at a time slot T, and we denote it by day here. So thus we can have number of vehicles here, number of vehicles, and they can have let's say the intermediate stage recharging for the set B during this hour, 15 hour here. So that thus we can know how much is the energy demand, how much is the energy demand in a given traffic zone at a time slot 15 hour. We can know this. So then we work on with the second optimization problem to evaluate what is the final price and which is to be paid in the trading system for each traffic zone for each period. And we have the second objective function, so to minimize the total cost of energy exchange for the all the vehicles in every traffic zone and for every time slot. So we have this equation, the objective function defined. That means for each time slot, the price for each vehicle, it is set from the owners of set A. It is given by this relationship, and the terms are what is the price being paid to the ith vehicle, what is the energy extracted, then what is the price curve. In fact, if you refer to this figure here, so what is the possible energy price peer-to-peer trading and the amount of energy which is to be shared. So if there is some linear relationship as defined with this one, so that will define what is the amount of energy that can be shared. And then we have the maximum and minimum price to be paid to the ith vehicle of the set B, and then what is the amount of energy available to be exchanged and the number of vehicles. So with all these informations, this function can be optimized. So here again we have set uh, some given set of points that satisfies this relationship. That means this will be the amount, and then this should be greater than how much energy to be demanded for a given traffic zone at a given time slot. So this is a quadratic programming formulation, and with this we worked on with the object cost function as defined in this relationship, and with the linear restrictions on the amount of x here, because x what you refer, it is the amount of energy available to be exchanged. So this for each vehicle it has been defined, and with this case we have some result for individual analysis to show. So we have said that the initial amount of energy which can be shared, it is 0.19 kilowatt hour, and you can see here that this was the electricity price in the morning at 6 o'clock, and this is the energy which is available in the battery of the set A. And however, the I can see that electricity price, this is how it changes, and this is the energy of the battery which is changing here. And then the peer-to-peer electricity price, it is this one, right? So now with this, now vehicles from the set A, they will not be able to share the energy when they are driving, because that means when the vehicles are in motion, then they cannot share their energy actually. So this peer-to-peer electricity price during this time zone, they are actually zero, as you can see, right? Because the peer-to-peer electricity price, it is zero during this period, because during this period, the vehicles of set A, they are in motion. So they cannot exchange, they cannot have trade during these periods. And however, during this period, the vehicles, they are parked at their destination. So there they can have the energy trade, peer-to-peer energy trade. That is possible. And you can see that we have the greatest demand for buying energy for the set A during this period. So you can see that peer-to-peer price is this one, our electricity price is this one, and that is the max. We can say the maximum demand for buying energy because it is this period here. Because here the electricity price is low and the peer-to-peer price is this one. So that will be could be the maximum or the greatest demand for buying energy of set B owners here, right? And then if you refer to the electricity price analysis for this zone, you can see that in fact here they have defined an energy ratio. What is the total energy, which is actually the ratio between the total energy demand from the B to the total energy available to share from the set A in a given zone and at the same time slot. So they have considered different traffic zone. As you can see, they have referred as low ratio, medium ratio, and high ratio. So what is the low ratio? In fact, that is, you can say, the maximum energy available, which will be shared, because this value is ratio is unity. So that means total energy demand and the share energy available to share. This is unity at this time slot. So the low energy ratio, let's it is for traffic zone 2350 number, and here we find there are more electric vehicles because it is a blue curve represented. So we have more electric vehicles which are able to offer energy than the electric vehicles demand here for recharging. So thus in this zone, in this traffic zone, there are more number of vehicles. There are more number of vehicles which are able to offer energy, more energy than the demand for recharging actually. During this, this is just an example here. So this will be the curve here. Then if you refer to the medium ratio, as you can see some green representation curve. So here in this case, they are slightly increased, the ratio is increased, and it is particularly during certain periods here actually. And they have an average ratio of something 7.49 something here, because that is the average here, but with the peak value of 34.2% here something. It is this one. So this is the medium ratio. Then for the high ratio, when you look at it, is this one. So with this case, traffic zone number 1824, they have average ratio of 9.41 something, and but also have 100% here. That is the highest value, which is somewhere here. So that means during this period, whatever the energy demand, it is all available to be shared between the two sets of electric vehicles here. And next, when you have this one, how let us analyze how the electricity price has varied. So for the different time zones, so it shows the P2P price for each of these zones. So they are all indicated with a different color. So you can see that for the low energy ratio, which was with the blue curve, the P2P price in this ratio is almost constant, and it does not vary here. And the value is something 27 euro per megawatt hour. And however, for medium ratio zone, in this case, it has reached to much higher during these time slots. And when you refer to the high ratio during this hour, it has reached much higher during this one. So because here you find that it is it should be equal, because during this period the delivery price should equal to grid electricity price basically here at this point. So finally, the conclusion in the study, we had observed
हेलो सर। विजय सर,
Yes, sir.
एक्चुअली यहाँ थोड़ा नेट कनेक्शन हो गया था तो थोड़े के लिए हम डिस्कनेक्ट हो गया था, मुझे लगता है तभी सर का ओवर हो गया।
ओके, वो फिर बाहर चले गए, हमको लग रहा है वो है। हम्म, ओके।
लाइट चली गई थी ना यहाँ पे, तो नेट भी डिस्कनेक्ट हो गया था।
अच्छा, so is there is any announcement for the next session?
यस यस, द नेक्स्ट सेशन विल बी स्टार्ट एट 2:30 p.m. which is the last session of today, and after then there is a
Mm-hmm.
validity approximately at 4 p.m.
So we can start validatory session after finishing of our the 14 session.
यस यस यस।
तो हम लोग तुरंत स्टार्ट कर सकते हैं, जैसे ही वो सेशन खत्म हुआ तो इसकी कंटिन्यूएशन में वी कैन डू इट।
ओके 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 सर।
हम्म।
ओके
So I hope कि अभी सर ज्वाइन फिर whether you have tried to join or not?
सर, नो नो नो।
No, okay. ओके सर।
हाँ ठीक ठीक ठीक, एक बार सर से फ़ोन कर लीजिए ना, हो तो एक फ़ोन कॉल आ रहा है।
ओके ओके ओके। हेलो, गुड आफ्टरनून सर।
I'm not sure. I think I was disconnected
यस सर, यस सर।
when it was.
सर 2-3 minutes later sir.
Acha, 2 3 minutes back. Okay, okay. But I completed my presentation.
Yes sir, yes sir, actually we have some queries in our chat box.
Okay, okay, okay.
How much price of grid differ during night and day?
Okay. Now, if I have to talk in respect to this example, right? If you look at, I think maybe I would share one of the slide here. Uh, I would share it. Can you see my screen now? Yeah, Vijay.
Yes, sir.
Yes,
Yes,
sir. Yes,
sir.
sir.
So if you look at this example, which they have it from the Flanders region, because this is the electricity price on the right hand side scale. So it was something 30 something 37 euro per megawatt hour, and that was the, you can say, the least electricity price, and it is during the night hour basically, or in the morning itself. And the maximum electricity price was something 68 or 69 megawatt euro per megawatt hour. So that is the range, so you can say. So it varies from 38 to 68 something. So 30 euro per megawatt hour. That is the range, I can say, between the maximum and the minimum value in the electricity price. Right? In this example, it is this.
Okay, thank you, sir. And one more question.
Mm.
If set A charge battery of EV from grid price, then why set A exchange the extra power of battery to other vehicle at low price than grid price?
Okay.
You can see, sir, in chat box.
Yeah, yeah. Okay, I got it. I got it. Wait. I can say that. Okay. Now, if you look at this figure, right? If you look at this figure, right? Now, just see, the owners of set A, they have paid different electricity price. Okay, agreed? So they have it, the maximum electricity price which they have paid, it is something 38 euro per megawatt hour. That is the maximum energy cost which they have paid for charging, right? And the minimum which they have paid, it is something 8 euro per megawatt hour. That is the minimum which they have paid it, right? Okay, but this difference, if you refer to the blue dash line, this is set at this value, the maximum value. This is not set somewhere here, right? So that means the profit which they already set, that this much profit I should have, it is with respect to the maximum energy which they have paid. Actually, maximum cost of the energy which they have paid, it is not with respect to the minimum cost of the energy which they have paid. You understand? So anyhow, they keep their margin, they keep their threshold that this much should be the profit. It is with respect to the maximum cost of the energy, it is not with respect to the minimum cost. So if they keep it with respect to the maximum cost which they have paid, so definitely they will have some profit out of it. So that's why it is said that this blue dash line, it is with respect to the price which they have paid it, and it is the maximum one. we we don't have, and we have said this is constant throughout the day, we will not vary it. Now if they keep it here, then definitely their profit could be lower, it could be lower. But this scale they have kept it towards the maximum price which they have paid, not towards the minimum price which they have paid it. So definitely they will have some profit out of it. You get it? Because now it is, because whatever the amount of energy which is stored in their battery, this is also the price which they have paid. This is also the price, and with this respect, they will have more profit. They will have more profit, but they say with respect to the maximum one, because that is the higher level. Actually, you can say. Agree?
Thank you, sir. Thank you. Uh, so I think there is no more questions from the participants. So once again, I thank you, sir, for giving such an informative talk on the peer-to-peer on electric vehicles. Thank you once again, sir. Thank you.
Thank you. So I can log out now?
Yes, sir. Sure. Sure.
Okay. Thank you. Okay.
Thank you. So for the last session of our the day, we will again resume at 2:30. Thank you. Patel sir, please stop the recording.